Okay, so we are moving on from the technique of substitution to another uh, technique of integration called integration by parts. This is section 5.6. And I wanted to just show you there's a formula for integration by parts. And the formula is and you can blow this up by using your zoom in feature on the top left. You can zoom this document. But let me see here now. Hold on. The integral of u dv equals uv minus the integral of v du. That's the integration by parts formula. And I'd like you to see where that comes from. So the way we begin is well, they mention that every differentiation rule has a corresponding integration rule. Okay, and what we're doing here is we're looking at the derivative of the product rule. So the derivative of the function f times the function g would be, I like to think of it as f prime times g times, well, what I'm trying to say is this, so the derivative of a product of two functions, I always think of it, write it as f prime times g plus f times g prime. But they're writing it a little bit differently. They're just writing f times g prime first, plus then the f prime times g second. Now what they do here is they say, okay, here's the quotient rule. That's fine. There's the quotient rule. What if I were to integrate both sides of this equation with respect to dx, of course, with respect to dx, right? Well, on the left-hand side, you're taking the integral of a derivative. So those are reverse processes, right? The inverse of a derivative. So that would give you just f times g, which they write on the right-hand side. Okay, I don't know why they don't leave it on the left-hand side, but they just decide to put it on the right-hand side. Well, I know why, but they kind of do two steps at once here. And then on the right-hand side, you have the integral of f times g prime plus, well, you have the integral of the quantity f times g prime plus g times f prime. But the integral of a sum is the sum of the two integrals. And if we leave this first integral alone on the left-hand side, in other words, if we leave this first integral here, and then bring that second integral over to the right-hand side, we'll have the integral of f times g prime dx equals f times g minus the integral of g f prime. That's called the formula for integration by parts. That's called your integration by parts formula. And what you can do, what they do is they say, well, they want the formula for you to be easy to remember. So yes, we have the integration by parts formula right here. But if you say, well, let u equals f of x, okay, and when you do that, du dx equals f prime of x, so du is f prime of x dx. Okay, and so this, for instance, here, this f prime of x dx, we can replace that with du. Similarly, if we let, so that was letting u equal f of x. If we let v equals g of x, if v equals g of x, then dv dx is equal to g prime of x, and therefore dv is equal to g prime of x dx. All right, and so you see here, the g prime of x dx, that's dv. So you have on the left hand, and of course, the f of x we set equal to u, right? And the g of x we set equal to v. So it turns out that then the integral of u dv is equal to uv. I don't know why, so please don't draw circles. I don't know what's going on the top left hand there. I want everybody to be able to write, if they need to, because when students have questions, sometimes they have to circle things in the notes. All right. So the integral of u dv equals uv minus the integral of v du. And that's your integration by parts formula. And we derived it, and now we're going to make use of it. We're going to make use of it to help us do some integrals. And this is important, for instance, with integrals that come up like in differential equations, Math 282. It comes up a lot. Are there any questions? Any questions on that?
Does the same go for quotient rule?
Well, we don't have it's a good question, Lillian. We don't have a rule that I'm aware of that corresponds to the derivative of a quotient rule, but I'm sure we could come up with something. But generally, they don't like have a formula that they use for that.
Okay.
All right. Well, so, okay, let's look at a problem. Now, a lot of times integration by parts is helpful when you have the product of two dissimilar functions. So Javier, that's in your book. That what I just showed you here, all of this is in your textbook. So I wasn't expecting you to really produce it in your notes, but did you have to? I should have mentioned that in the beginning. Did you have a question? Is everything clear? All right, so all we wanted to do was establish this integration by parts formula here. That's all we wanted to do. And this is that's in your book, so I'll let you look at that if you need to refer to that. Oh, I see. Well, Javier, you'll have to go. Okay, I see. I'm sorry about that, but it'll be in the recording. Those like notes I was making. I see what you're saying, like with the marker and stuff. Okay. I'll be more cognizant of that next time. Okay. You can go back to the recording and see that to fill in the notes then for yourself. But I'll be a little more cognizant of that next time. All right, well, very good, very good. So here we are. We have the integral of t times the sine of 7t dt. So one of our functions is t. The other function is the sine of 7t. Now, do you think substitution would work here? Can I let u equal, can I do like a strict substitution? Would that work here at all? Is sine of 7t connected at all to t? Is there any connection between those two functions? No. So substitution is not going to work here. Integration by parts, though, can work here. So remember integration by parts. The formula is integral of u dv equals u v minus the integral of v du. So when you do integration by parts, okay, when you do it, the integral that you're working with corresponds to the left-hand side of the integration by parts formula, the integral of u dv. So what we have to do is we have to let u equal something, and we have to let dv equal something. So in other words, this integral is going to be equal to the integral of u dv. But what's u going to be, and what's dv going to be? Well, and I got to be a little, hold on, I got to be a little more careful here. The sine of 7t dt is we can't forget about the dt. Well, I'll tell you what. I'm going to try, Shalom, letting u equal t. So let me go to the next page here. I'm going to let u equal t. All right, and there's a reason why I do that, because if u equals t, du equals dt. It simplifies a little bit. Right? So, one moment. So, all right, u equals, let me just use my highlighter up here. So u equals t, and dv is sine of 7t dt. So this here, the sine of 7t dt, is my dv. Okay, so that corresponds now to the left portion of the integration by parts formula. What I have to do to write out then the right-hand side of the integration by parts formula is I have to figure out then what du is, and I have to figure out what v is. Okay, well, if u is equal to t, du is equal to dt. But if dv is sine of 7t dt, it turns out that v is negative cosine of 7t over 7. Now, why would that be true? Well, on the over here, I've done a little check on that. I mean, put it this way: I'm telling you that v will equal negative cosine of 7t over 7. Is it that true? Well, let's check it out. I'll take the derivative of negative cosine of 7t over 7 with respect to t. We use the chain rule, right? We use the chain rule. So the negative 1/7 I bring that out front, and the derivative of cosine of 7t by the chain rule is negative sine of 7t times 7. So dv dt then would equal sine of 7t, and therefore, I mean, that's what dv dt is, and therefore dv is sine of 7t dt. So it checks out. It checks out. If v is negative cosine of 7t over 7, then dv will be equal to sine of 7t dt. So essentially what you need to do, to go from the sine of 7t to the negative cosine of 7t over 7, what is negative cosine of 7t over 7 relative to the sine of 7t? Negative cosine of 7t over 7 is the what of sine of 7t? It is the
Repeat the question.
Oh, let me phrase it another way. Okay. I'm gonna phrase it another way. Antiderivative. That's right, Daniel. That's Jonathan. That's correct. What I'm trying to say is the derivative of v is equal to the sine of 7t. So the antiderivative of the sine of 7t is equal to v, which is negative cosine of 7t over 7. So in other words, to get v from dv, just take the antiderivative. That's what I'm trying to say. That's what I'm trying to say. And so now I'm going to utilize the integration by parts formula. I know what du is. I know what u is and v is and du is. I know it all. So now I apply the formula right here. And the idea is, hopefully with this formula, I can break down the integral so I can figure out so I can get an antiderivative. So the integral is uv, right? U times v, minus the integral of v du. So integral of u dv is equal to uv minus integral of v du. Well,
Professor? He's on the scene and he's a plan. Professor?
Yes, Claire?
So, so like for the dv, it's sine of 70 dv, and we have to find the antiderivative. But isn't the antiderivative of sine minus cosine? So why do we have also the 7 down? Like minus, I don't get the 7.
I'm having a little trouble hearing you, Claire. Okay, that helps. What were you saying again, please ask?
So when we find the antiderivative, why do we have minus cosine of 70 over 7? Isn't only because the antiderivative of sine isn't only minus cosine?
The antiderivative of sine is minus cosine, but you have that 7t there. So you have to make an adjustment. You have to adjust it by putting a 7 in the denominator.
Okay.
Yeah. You have to, if it were just the antiderivative of the sine of 1t, you'd have negative cosine of 1t. That's correct. But because you have the 7t there, you have to make that adjustment.
Okay.
Okay. So getting some background noise here. All right, great. All right, so, well, okay, so it turns out that, let's look at this, the integral of cosine of 7t dt. I just say, hey, it equals sine of 7t the antiderivative of sine of 7t over 7. Let me just go to the whiteboard real quick. I want to just do something real quick. So okay, so this is your, integral. So if you wanted to just do a little substitution, let u equal 7t, then du is 7 dt, and then dt is equal to 1/7 du. So that means then this integral is going to be the integral of cosine of u times 1/7 du. Well, that's 1/7 times the integral of cosine of u du. Okay, now this is not, this u here is, this is just a separate thing, what I'm doing here. I'm trying to justify that antiderivative. So the antiderivative of cosine of u is sine of u. And now we'll put back in the 7t. Parentheses are optional, but so you see the antiderivative of cosine of 7t dt is indeed 1/7 times the sine of 7t. So, pretty soon, like, you're going to be able to look at something like the integral of the cosine of 7t dt and know that the antiderivative is sine of 7t over 7. You're not going to have to go through this substitution that I did. But that's just a quick justification on that. So let me go back to the problem here at hand. One moment. Okay, so here we are. And now we have our answer. We have our integral. That is the answer. That's your antiderivative. Pretty cool, huh? Pretty cool. How many think this is kind of cool, what you just did here? Okay, Daniel's liking it, and Mark's liking it. Okay. Good, good. Are there any questions? I'll mention something because I know I just came. So you might wonder, how did I know to let u equals t and dv equals sine of 7t dt? Well, the way I knew, I'm trying to break the integral down to make it, I'm trying to dissect it into simpler parts, so to speak. And the fact that my integral was cosine of 7t dt, and I could integrate that, tells me that this was the right choice. If I had let u equals sine of 7t and dv equals t, we would have ended up with a more complicated integral when we did the integration by parts. So if things are getting more complex, then your choice of u and dv are not the right choices. And the only way you can sort of get a feel for this is with the practice. Okay, are there any questions? Susanna?
Yes, you mentioned it briefly, but how can we be sure again that substitution wouldn't work? And this, I'm sure they'll get more complex. So just as they get more complex, what how do we know that substitution is not relevant?
Well, in this problem, your integrand was the product of two very dissimilar functions, t and the sine of 7t. Those two, the function t and the function sine of 7t, have no connection to each other. So making a substitution on one of those functions and isn't going to get me the other function. I'm not going to be able to I'm not going to be able to manipulate it with substitution. So generally, if you have I'll tell you what, let's look at another example. Let's look at another example. I think another example will be helpful, but this is the final answer on this one. It's a very good question, very good question. Let me see here, hold on. Yeah, I think I'm going to do this one next. All right, let me find it here. One moment. Let me find this. Okay. So now, like you see in this problem here, you have the integral of, well, what's your integrand? You have a product of two functions, e to the negative theta and the cosine of 2 theta. Are those two functions, like, is there a relationship between those two directly? No, no. Remember the one problem that we did, actually the substitution problem. We had the integral of the arc sine of u. I believe that, let me just make sure I have it right. Yeah, we had the, hold on. Find it here. Yeah, we had the integral of the, well, let me rephrase it here. In that substitution problem we did, we had the integral of 1 times the square root of 1 minus u squared times the arc sine of u, okay, du. So these were your two functions. Here was the one function times the other function. Was the arc sine of u, does the arc sine of u have a relationship with the function 1 over the square root of 1 minus u squared? Is there a relationship between those two functions? There is, absolutely. We know that, that's right, Shalom, that's right, Opayemi. We know the derivative of the arc sine is equal to 1 over the square root of 1 minus u squared. So that's why substitution worked there. However, in this problem, there is no direct connection between these two functions, e to the negative theta and cosine of 2 theta. So this is an example where integration by parts could provide us an answer, could help us. The question is now, what do you want to let u equal, and what do you want to let dv equal? So let's remember now. Let's remember, we have to consider. I mean, what we're trying to do is we're trying to write this integral as the integral of u dv. Okay, And so the question is, what is U going to be, and what is dV going to be? Okay, and oftentimes there's only one right choice that'll work, but sometimes you can get something different. And I am hearing folks, several people said let U equal that e to the negative theta. And I will tell you that would work. But what I'm going to do is instead, I'm going to let U equal cosine of 2 theta. And then the e to the negative theta d theta, okay, those together, I'm going to let be equal to dv. Okay, and I want to see if it'll work out. So if u equals the cosine of 2 theta, du d theta is, by the chain rule, minus sine of 2 theta times 2. And so therefore du is equal to minus 2 times the sine of 2 theta d theta. That's how I get this. And then the antiderivative of e to the negative theta is negative e to the negative theta.
I have a quick question. Why are you doing the chain rule for -2 sine theta?
For
The derivative of u.
you mean like right here, the derivative of?
Yeah, for the derivative of u. You took the derivative of theta over du. I understand that part, but why are you doing the chain rule to the negative sine 2 theta?
Well, so there's two functions here. There's the outer function is the cosine function. The inner function is the 2 theta. So the derivative of the cosine is the minus sine.
Mm-hmm.
And then the derivative of that 2 theta, that inner function, is just 2.
Oh, okay.
All right, very good. Good question. And if you, like, in terms of the if you want the antiderivative of e to the negative theta d theta, that will equal e to the negative theta over -1 plus a constant. So yeah, that would be v then. So now look at what we do. So we have the integration by parts. So you notice how the integral, I set it equal to I in the beginning, and you're going to see why that it's very helpful here. So let's see, we got v u here. Okay, so again, the integration by parts, let me just write the integral of u dv is equal to u times v minus the integral of v du. All right, that's that integration by parts formula. So, okay, well, u and v are here. Okay, so that's the uv part. minus integral of v du. Well, all right, v, hold on here. Yeah, this here, the 2e to negative theta sine 2 theta d theta, that is v du. Absolutely is. Because if you take the v here and multiply it by the du here, you'll get this. And what I do is I say, okay, so I have to find out what this integral is. So, I factor that 2 out, and now I'm at the integral is equal to this expression here. But what happened? Well, look at the integral. You have the integral of e to the negative theta sine 2 theta d theta. You have that integral right here. Is that integral any harder than the one we started with? It's not any easier, but is it any harder? We don't want our new integral to be harder. It's about the same level of difficulty, right? So, but I don't have an answer. I don't know what my integral is because I have this, I have this I got to find the antiderivative of e to the negative theta sine of 2 theta. So look what I'm going to do here. I'm going to do integration by parts again. Okay, I'm going to let u equal, or we're going to let u equal sine of 2 theta. Du will be 2 cosine 2 theta d theta. Okay, so this is going to be u. And then dv is e to the negative theta d theta. That's what dv is. Maybe I'll put it in a little bit different color. Maybe green. Okay, this here be your dv. And so we're doing a second cycling of the integration by parts. We're doing integration by parts twice. Now you might wonder, well, why are we doing that, Dr. Dewey? It didn't work the first time. How's it going to help us the second time? I mean, look what happened. You have v times u. Okay, this part here is minus the integral of v du, and that is correct. So I mean, what we have here is we have the integral of e to the negative theta cosine, hold on. Okay, so I have the integral of e to the negative theta cosine of 2 theta d theta, all being equal to what's on the right side here. So you have an equal sign, right? So it's just going to keep repeating, right? But yet I can solve for my antiderivative. I can solve for the integral of e to the negative theta cosine 2 theta d theta. I can solve for it. Because, well, I have an I here, and then I got I back again here. Right? So what can I do with the I terms? What can I do with those integral terms?
Cancel them?
Well, hold on, there's some background noise. Sorry, thank you. So there's a 4 here. So if they're, Clea, you're on the right track. I wouldn't say I can cancel those because I have an I on the left side of the equal sign, and then I have an I term on the left side of the equal sign, and then a negative 4i term on the right side of the equal sign. But what can I do with those I terms?
You could set them equal to each other.
Well, are you thinking, you mean combine them? All right, John, that's right. So I think you, Shalom, that's what you're thinking about. Yeah, John's saying add 4i to both sides, and that's correct. That's correct. Here's what we have. And I am going to add 4i to both sides. I'm going to add a 4i here, and I'm going to add a 4i here. These will cancel. And 1i plus 4i is equal to 5i. So 5i will equal negative e to the negative theta cosine 2 theta plus 2 times e to the negative theta sine 2 theta. And now what I'm going to do is I'm going to get the I by itself. I mean, I was my integral, right? My integral is equal to I. So at this stage here, I can just multiply by 1/5 on both sides. And then I bring in my constant of integration, and now I have my answer. So it turns out that the antiderivative of e to the negative theta cosine 2 theta will equal negative 1/5 e to the negative theta cosine 2 theta plus 2/5 e to the negative theta sine 2 theta plus a constant. This is a very important antiderivative because you're taking a cosine function, a trig function that oscillates back and forth, and you're multiplying it by a dampening function, e to the negative theta. Okay, so like think of a mass spring system where you have a mass that's oscillating up and down, but then you have a dampening factor on it to have the oscillations dwindle down to 0. I mean, this is a very common kind of function. So certainly we want to know its antiderivative. How many think this is like maybe one of the coolest problems, coolest solutions you've seen so far in calculus? Okay, Daniel's liking it. That must be. It's like, well, it is hard because it's the first time you've seen it, and you're not. It's like, weightlifting. You're used to picking up a 50-pound barbell, but now you're doing a 60-pound barbell. It's but I mean, it's really a beautiful result, right? It's really quite amazing.
Professor, I have a question.
Yes, Nia.
Oh, could you go back to the previous page?
Okay. Is everybody good with this? I'll go back. Has everybody copied this? Okay. I want to make. I'll go back. I'll go back.
Or I can just ask it anyway. So the question was the integral of that. I don't know how to read this. Anyway, if we had if we had interchanged the u and the v, would it have been less complicated?
It would be. There's no way to get out of it. In other words, what Niat's saying is, back when we did the u, we assigned u and dv. If we were to let u equals e to the negative theta and dv equals cosine 2 theta d theta, if we changed our assignments there, you would still have to integrate twice to work the problem. Yeah, you would. You would
All
get
right,
a
thank
field medal in math if you could do this problem with one light. This problem, I've seen it a long time, and it always takes 2 integrations to work it. All right, good question, good question. Okay. I'd like to look at one more example, and I think hopefully you'll have a little time here to work on some on that next assignment. So there are the integration by parts assignments are going to be due next Wednesday. I may make an adjustment on one of them because we're doing some good problems, integration by parts, but I think we need to do yet still a few more. So I may leave the password on one of them and then adjust it and then take the password off. But all right, well, let's go to another example then. Let's go to this third example. Let me just find it here. No, wait, hold on. Okay, take this off. I got to find the example. So, you know, the book has good examples. I'm trying to add to those examples. Sometimes I do their examples for sure, but I also try to add to the examples, do different examples with you so you get a wider variety. All right, so let's take a look at this problem. Let me give you a moment to copy it down. So this is kind of an interesting problem. We want the antiderivative of this arctangent of 4t dt. So here you don't have two functions. You have just one, the arctangent of 4t, okay, dt. And you know, like the previous two problems, we had the product of two dissimilar functions, and we used integration by parts. So I'm going to show you how to handle this kind of problem. Let's go to the solution. So what we're going to do is we're going to let u equal the arctangent of 4t, and then dv is just going to equal dt.
What the fuck?
Sorry, I'm getting a little background noise. Shalom, is that you?
No, it wasn't me.
Okay, okay. So generally, class, you want to have your, your mics on mute, and then of course when you, all right. So, all right. So one of you needs to. I don't think you need to be playing music now, right? This is. I like Rihanna just as much as you and Beyonce and the Oak Ridge Boys. I love them all, but we're doing our math now. So let's see here. So, okay, u is the arctangent of 4t. Thank you. U is the arctangent of 4t. dv is dt. Well, this means then that then v would have to equal t. And by the chain rule, we differentiate u with respect to t, and then du is equal to 4 plus 6 over 4 divided by 1 plus 16t squared dt. So again, here's the integration by parts formula on the top right here, and we're just gonna do it. And we know this is gonna, if this, of course, what do we have to do? Well, we have to integrate this. We have to integrate this. And this is being recorded, so the recording will be available. Mandy, I can, if you can stay a moment after class, I can address that question that you have, okay? All right, so this is where we are. Let me deactivate my email here. I don't want any distractions here. Okay. So, okay. Well, what do you think about this integral here? How are we going to, what approach is going to be good there? Integration by parts or substitution?
Personally, I think substitution would be more efficient.
Okay. And integration by part, I agree, Clea. Integration by parts, incidentally, might not work at all. Well, all right, if we're going to do a substitution, I'm not going to say u equals, I'm going to say w equals, because we have u and dv being, we use those variables for integration by parts. What would you let w equal? What would be maybe a good choice?
1 plus 16t squared.
That's absolutely right. Very good. 1 plus 16t squared. Let's take a look. Well, Javier, how would you know to use substitution or integration by parts? Experience and practice. So that's why it's very important to do the homework, so you see enough problems so that you have kind of a intuitive feel. How many like Star Wars movies? How many are Star Wars fans here? How many are like Okay, Ivor likes it, Mark and Say it, and John. Yeah, you know, in Star Wars, and oh, have you ever watched all the movies? And you know, you have the Force, right? So the Jedi's are good with their swords, and because they can feel the Force. So that's kind of like, well, honestly, what this is. How do you know whether substitution or integration parts is going to be good? You develop a feel. You develop a feel for it, and that comes through Jedi math training, practice, right? Doing homework. All right, so we will make a substitution. I will tell you generally, I always, when I'm encountered with an integral, I always first think, could a substitution work? Because substitution, in my view, is easier than integration by parts. It's a little easier. So I always look first to substitution, and then, yeah, Mark agrees. And then if substitution isn't obvious to me, I'll try integration by parts. So that's a little guidance there. Okay, well, W is 1 plus 16t squared. So then it turns out that, so let me just make a note here. So the 1 plus 16t squared is W. So that means then I got to figure out what t times dt is. Well, t times dt turns out to be 132 1/32 dw. Let's see, Mark. Well, yeah, I mean, integration by parts is a little harder. It's harder. So, okay, well, all right. So this is our resulting, let me just see here, hold on. This is our result then. And I'll bring the 1/32 out in front. And the antiderivative of 1 over w is, as you know from Calculus 1, the log of the absolute value of w. So this is we have an antiderivative now. And is this what you're going to be typing in WebAssign? Is that the final answer? T times the arctangent of 4t.
No, you need to convert the W.
That's right. Good, good. Shalom, good Yonatan. We need to substitute in the W, because remember the original integral was an integral with respect to the variable t. So my answer has to have t variables in it.
Professor?
Yes, say it.
What if we like kept the constant 4 in the antiderivative, like to keep like 4t over 16t squared plus 1, and then directly see that as like d of u over u?
So you're talking up here? Up.
Yeah, like here.
Yeah.
And then from that, like directly like go to like, because we know that like d of that would make like equals to 1 over 8.
You're saying could you get the antiderivative just like maybe looking at this, you know the antiderivative. I gotta be honest, for me, I would not know the antiderivative offhand. I think you need to make that substitution just to show the work out and stuff. Are you saying you can look at that integral and sort of figure out what the antiderivative is?
Yeah.
By observation?
Yeah, because like I kind of remember like a formula with like the logarithm.
I understand what you mean. I would prefer that for this, that and sometimes that is definitely the case, but I think this, I would prefer, like on your exam, that you show me this kind of work here. I know it's extra work for you, but it's good for the soul, as we say, and you know, it isn't that hard. It isn't that hard. But
All right, I see.
yeah, I understand though what you mean. I do. I do. All right, well, let's get the final answer then. Are there any other good questions? All right. Well, then let's proceed on. So we have to replace the W, and W was equal to 1 plus 16t squared. And so, all right, I put in the W, and I can drop the absolute values. Why is that? Why can I, like, the log of the absolute value of 1 plus 16t squared is the same as the log of 1 plus 16t squared. Why can I drop the absolute values? You can't always do that, right?
Yeah, since there's a t square, so we always get a positive number.
That's exactly right. Very good, very good. So, okay. Well, here's our answer then. The antiderivative of the arctangent 4t dt will equal t times the arctangent of 4t minus 1/8 minus, let me say it again. The antiderivative of the arctangent of 4t equals t times the arctangent of 4t minus 1/8 times the natural log of 1 plus 16t squared plus a constant. And if you were to differentiate that right-hand side there, if you were to differentiate this right-hand side, you would end up getting the arctangent of 4t. I mean, you could check to see that it's true, but it's true. So you've seen here three very good problems for integration by parts. And I hope they will be helpful for you. Are there any questions? Okay. Well, then I will stop the recording. And all right.